Hey everybody, it's Mr. Campbell with Mathematical Anarchy, and today we're going to be talking a little bit more about functions. Specifically, we're going to focus on how to use notation, how to evaluate a function, and how to find initial values. To start, we're going to take a look at function notation. Like most notation, we're going to use symbols to express a lot of information in a small amount of space. Right? Mathematicians like to conserve space. Probably came from not having a lot of paper to write on hundreds and hundreds or even thousands of years ago. Okay, so being able to say a lot of information in a small amount of space is very useful. And so here we're going to be expressing the relationship between the inputs and the outputs of a function. We have a mathematical statement below, y equals f of x, and that's how we're going to say it, y equals f of x, because y is a function of x. And from what we know, x is going to be our input, and so we can see that's on the inside, corresponds with the independent variable, and y is the output. That's on the outside and corresponds with the dependent variable. For our first example, we'll take a look at a verbal function. Profit, P in dollars, is a function of the number of gold cards sold, N. So if we translate that into symbols, P is a function of N, P equals F of N. We can shorten that to just P of N. In both cases, N is on the inside, it's the input, P is on the outside, it's the output. So taking a look at a specific numerical example, 100 equals F of 20. The 20 is on the inside, that's going to be a number of gold cards. So 20 gold cards sold, the 100 is on the outside, that's a profit. So $100 profit for selling 20 gold cards. It's going to look like P of 20 equals 100 using the other notation. What I like about this one is it specifies the variable P. Okay, but in both cases, the 20 is on the inside, the 100 is on the outside. And both of them represent the verbal statement that selling 20 gold cards will give a profit of $100. So in both cases, again, we're expressing a lot of information about the situation using as little space and symbols as possible. Now, for our next example, let's say we wanted to pour a concrete slab. You want to pour a concrete floor for some reason, 4 inches thick. So the amount of concrete, C in bags, is a function of the area covered, A, in square feet. So we can express that C equals F of A or C of A. In either case, A is on the inside, that's the area, that's our input. So we can look to our table and know that the 25 on the inside of C of 25 is going to be a square footage. So trying to figure out what C of 25 is, okay, well, that's going to be the number of bags of concrete that we're going to need for a 4-inch thick slab, and that's going to be 19. So C of 25 equals 19. And our verbal description, a concrete slab 4 inches thick with an area of 25 square feet needs 19 bags of cement. So again, expressing this in function notation saves a lot of space. And what we've actually done by finding the output that goes with the input is we've evaluated the function. For our next example, we have a graph that represents the number of F-35 planes produced as a function of the year. We can write that P equals F of T or P of T. Again, the year is on the inside, that's our input, P is on the outside. The number of planes, that's our output. So express the number of planes produced in 2017 using function notation. Well, we know that 2017 is going to be our input, so we can go ahead and put that inside our parentheses. P of 2017 is, what is that equal to? Well, the number of planes produced, which was 66. Okay. So again, we've evaluated the function and expressed it using function notation. Our next example is also a graph. This one represents the number of Americans incarcerated in prison, P in people, and jail, J in people, and these are both functions of the year. So we have two functions here that we're dealing with, P of t and J of t. So when we look at J of 2000 minus J of 1980, and we want to interpret what this statement means, we start with J of 2000, which is the number of people in jail in 2000. And we can estimate that on our graph at approximately 0.7 million or 700,000 people. And we're going to subtract off from that the number of people in jail in 1980. And we can approximate that as 0.25 million, quarter million, 250,000 people. So what we're really looking at is the change in the jail population between 1980 and 2000. Now substituting the values, okay, again, we're evaluating by finding the output that goes here. So we evaluate and substitute. We can go ahead and subtract, and we get 0.45 million people. So there's been an increase, and that's the equivalent of 450,000 people. Okay, so the jail size has increased by 450,000 people from 1980 to 2000. Now the next one, P of 2000 minus P of 1980, all over 2000 minus 1980. Well, P of 2000 is the number of people in prison in 2000. P of 1980, where we can estimate that at 2.2 million, and P of 1980 is the number of people in prison in 1980, and we can estimate that at approximately 0.6 million or 600,000. So what we're looking at is the change in population over change in time. That's our average rate of change on that time span. So we can go ahead and substitute. Again, we're evaluating by doing this. So we've got 2.2 minus 0.6 all over 2000 minus 1980. So we have 1.6 million people. Okay, that's an increase over a 20-year time span. So doing the division, we get 0.08 million people per year, and that is approximately 80,000 people a year. Okay, so between 1980 and 2000, prison population was increasing by about 80,000 people a year. For our last example, we're going to take a look at the height of a plant, h in inches, as a function of the time since it was planted, t in weeks, and it's given by the following equation. This one's an algebraic function. H of t equals 3t plus 5. So part A asks us to find h of 0 and interpret the value in context. So by seeing the 0 on the inside, I know that's a value of t, so t equals 0. So we're going to go ahead and evaluate the algebraic function by substituting 0 for every place we have t. So we have 3 times 0 plus 5, that's 0 plus 5, which is 5 inches. So it tells us that the plant was 5 inches tall when t equals 0, or when it was planted. In general, if we are looking for the output that goes with an input of 0, we call that output an initial value. So the initial height of the plant, 5 inches. Part B, what value of t will make the following a true statement? Now we're given an output, and we're trying to figure out what the input is. In general, we call this solving. So I know that h is equal to 26, so I can substitute where I see h of t. So 26 equals 3t plus 5. I can go ahead and subtract 5 from both sides to get 21 equals 3t. And then I can divide by 3 on both sides to get 7 equals t. And so that's going to tell us that it took 7 weeks for the plant to reach a height of 26 inches. So we've covered how to use function notation some of the benefits of using it. We've also talked about how to evaluate a function by finding the output that goes with a particular input. And when that input is 0, we call that output an initial value. So take a look at the practice, think about these ideas, see how they apply, try them out, and then come to class ready with questions. Good luck.